November 8th, at 2:24 in the afternoon Pacific Time. Fire broke out on the grounds of the Santa Susana Field Lab, the former Rocketdyne testing facility and Superfund site in Simi Valley, California, only 30 miles from downtown Los Angeles. The location where the fire started is only 1,000 yards from the spot where, in 1959, a nuclear reactor with an experimental salt-based cooling system melted down. That reactor was not housed in a containment structure, as nuclear reactors are today, but in an industrial shell building.
The Southern California-based 9th Civil Support Team responded to the Woolsey fire incident and confirmed there was no release of radioactive material. The National Guard has civil support teams stationed throughout the country that assist local first responders with identifying hazardous substances, assessing consequences, and advising on response measures. The California-based 9th Civil Support Team submitted a problem to the Hacking for Defense program hosted at Mines this semester. The problem stated that operators are placed at increased risk during reconnaissance of hazardous situations with their handheld equipment. Current ground robots take twice as long as operators and lack autonomous capabilities, while airborne systems are expensive and cannot take accurate atmospheric measurements. The operators need autonomous means to gather hazardous environmental information so personal risk may be reduced. Our team interviewed Civil Support Team operators and commanders to gain additional insight into their capabilities and pain points. We discovered they need an affordable, user-friendly device that is versatile enough to provide rapid initial information gathering and increase distance between operators and the hazard.
Our initial design started as a small, modular, low-cost sensor platform that could be deployed on land robots or aerial drones and report back to the operator. After some quick prototyping, we were able to get stakeholder feedback and iterate on our design. From our conversations, we discovered additional pain points that we could address and extended our solution to include mesh network capabilities and designed a 3D printed throwable casing. A solution that features multiple sensors dispersed across the incident site provides improved awareness and greatly reduces the physical risk to first responders. Our prototype is a self-contained cluster featuring a microcontroller integrated with sensing capabilities, Wi-Fi communication, geolocation, a camera, and a high-capacity lithium-ion battery to allow many hours of sensor cluster lifetime. Software is integrated to allow network communication between multiple sensor clusters, serving as a dedicated network for monitoring the environment, and is also capable of serving as a redundant communication pathway for operators when mobile networks go down. Our solution can now deliver vital information throughout any environment in real time and can be deployed on land robots, aerial drones, as a throwable, or placed stationary in a standby situation. Every emergency situation is different, so it is important that our solution is reliable and as versatile as possible to provide maximum utility. To monitor sensor readings on individual clusters, we developed a simple, easy-to-use GUI for first responders to analyze their environment in real time. It will alert users when and where a hazard is detected and observe network health.
Our versatile platform improves safety, speed, and awareness for first responders. It does so at a fraction of the cost of current handheld equipment, allowing for expendable deployment tactics. Low cost of individual clusters may eliminate the need for costly and time-consuming decontamination protocols. Sensor clusters can be used with little training by civil support teams or other first responders affiliated with National Guard teams. Currently, we're coordinating with civil support teams to design our product to meet their needs. These teams will be the early adopters of this technology. Once the product is in use with civil support teams, other first responder organizations will see the product demonstrated in regular joint training exercises. This brings us into our second target market. Since the initial first responders in crisis situations are generally members of fire and police departments, we believe this product would also be desirable for their organizations. Providing sensor clusters to affiliated fire and police departments will dramatically increase the initial available information when civil support teams are called into action. Lastly, we see future utility for this technology in the detection of hazards in industry, where maintaining a safe working environment is critical. In the first quarter of 2019, we've completed a prototype featuring mesh network capabilities as well as camera and GPS integration. As proof of concept for sensing capabilities, we've integrated temperature, radiation, pressure, and fine particle detection. In addition, we've designed and tested a throwable casing. Moving into the third quarter of this year, we will be developing a prototype with a ruggedized housing for the cluster, capable of communication at multiple radio frequencies. We will also integrate gas sensing in a prototype. In the fourth quarter of this year, moving into 2020, we plan to integrate 5 gas sensors, waterproofed housing, and self-propulsion. At this stage, we will have a scalable system ready for production. This technology has the potential to revolutionize first response and hazard detection. Operators using sensor clusters like these will experience improved speed, awareness, and safety.